Determine an expression for the strain energy stored in a solid conical frustum having maximum diameter d1 and the minimum diameter d2 of length equal to L, and the modulus of elasticity is E and the axial load is equal to P. Since here we have variable cross-sectional area, so we'll calculate here the strain energy for elemental area and then we'll integrate it. For this purpose, we'll use the strain energy formula, that is the strain energy U equal to integral 0 to L f square dx upon 2 times of area multiplied by young modulus E. So we'll consider here a section at a distance equal to x, and let's say the diameter at this section is equal to d, which one is a function of x. So here the diameter d is a function of x. We can develop a relation between the diameter at any distance x, d1 and d2 using a straight line relationship. So the diameter d at any distance x will be equal to d1, that will be the larger diameter, minus the slope. This time the slope is d1 minus d2 divided by L, and this whole thing is multiplied by x, that is the distance x. Since the diameter is variable, therefore area at the same section at a distance equal to x will be equal to pi by 4 into diameter at a distance x, and we have square of it. We'll put this value back here and we'll solve this equation. As far as the force P is considered, force P is constant at every section. So we have lower limit of x is equal to 0, and if I put x equal to 0, we have diameter equal to d1 at x equal to 0, and if I put here x equal to L, then L and L will cancel. We have minus of d1 plus d2, so d1 and minus d1 will cancel and we have plus d2, that is the diameter at distance equal to L. So this equation is correct. So total strain energy will be equal to integral 0 to L. Here the value of P remain constant, area is variable, young modulus is constant. So we can take out here P square divided by 2 times of young modulus. Instead of F, we'll use here P. So we have P square divided by 2 times of young modulus, and integral from 0 to L, and 1 upon area is 4 divided by pi, and we have dx square. Now here dx will be same as this term, that is we have d1 minus d1 minus d2 divided by L multiplied by x, and we have to make a square of this term, and this is to be integrated with respect to dx. This term is basically has a power equal to 2. In the numerator it has a power equal to minus 2 of dx. Integral of x to the power minus 2 dx is same as x to the power minus 2 plus 1 upon minus 2 plus 1, and if you have a composite function, then you have to again divide by derivative of that one. So here the denominator is minus 1. Let first here take out the common term. 4 is common here, so we have 4 times of p square divided by 2 times of pi divided by young modulus E divided by minus 1, so we'll write here minus 1. 4 pi already taken common. Then we have the derivative of this term will be x to the power minus 1. So we have to write this term as d1 minus d1 minus d2 divided by L multiplied by x, and the power of this term is minus 1 is further divided by the derivative of this term. Derivative of d1 is 0, and the derivative of this term is same as equal to minus d1 minus d2 divided by L. So derivative of d1 is 0 divided by, we have 0 minus d1 minus d2 d1 minus d2 divided by L, and we have lower limit here will be equal to 0 and the upper limit will be equal to L. So whole this term will shift in the numerator, minus and minus become plus. So we have 4 times of p square divided by 2 times of pi e. This L will shift in numerator, and in denominator we have d1 minus d2. This power is minus 1, so you have to write this term and you have to put the value of x equal to L. So in that case I will get the first term as d1 minus d1 minus d2 multiplied by L and is divided by L, and we have power is minus 1. Second limit I have to put, so we have minus sign, and this value you have to put the value of x equal to 0. So in this case only d1 is left, and we have power is equal to minus 1. So we have 4 divided by 2 is 2p square multiplied by L divided by pi multiplied by n modulus E into d1 minus d2. Then we have to write down the upper limit here. Upper limit is L here, so that will be get cancelled. We have d1 minus d1 is cancelled, minus and minus become plus. So we have d2 to the power minus 1 is 1 upon d2, and the second term here is 1 upon d1. Take LCM and solve it further. So we have 2 times of p square multiplied by L divided by pi divided by n modulus into d1 minus d2. Here we have LCM is d1 into d2. We'll cross multiply, you will get d1 minus d2. So at this stage this value is also cancelled out. So strain energy in the case of tapered bar is given as U equal to 2 times of p square multiplied by L divided by pi into n modulus E into d1 into d2. A uniform rod BC of length equal to L and the cross-section area A constant hangs under its own weight from a rigid support at B. If the rod is made of linearly elastic material with a modulus of elasticity E and the specific weight, that is the weight per unit volume, is represented by gamma, determine the strain energy stored in the rod in terms of gamma, n modulus, area and the length of the rod L. So let's consider here we have a bar BC of length equal to L and a uniform cross-sectional. It has a specific weight equal to gamma. We'll fix up our coordinate system, and let's say here the x-axis is upward. At bottom point we have x equal to 0. At top point, that is at B, we have x is equal to L. And we'll make a cut here for this section, and we'll develop the FBD for this bottom portion. So consider this portion below here which has a length equal to x. In this case the weight will act vertically downward. So this time here weight will depend upon the section that we have selected. So this time the weight is a function of length equal to x is same as equal to the specific weight gamma and is multiplied by volume. This time volume is same as equal to area, and we have length of section is equal to x. So this weight will responsible for the force here. So we have force is F, which one is again a function of x. So by equilibrium here f of x is same as w of x. So in this case we have f of x, that is the force is variable, is given as gamma multiplied by a multiplied by x. So total strain energy you can calculate again in the form of integral equation from 0 to L f square. This value of f is same as gamma into a into x multiplied by dx divided by 2 times of area divided by n modulus E. Area is constant here, n modulus is constant, that can be taken outside. So we have 1 upon 2 times area is constant, can be taken outside, n modulus is constant, can be taken outside. We have integral, and the limit of integral is 0 to L. F square will be equal to gamma square multiplied by area square multiplied by x square multiplied by dx. So gamma square is a constant value, a square is a constant value. So in this case we left here is 1 upon 2 times of area into n modulus E. Area can be taken outside, so we have a square into gamma square, and we have integral from 0 to L of x square dx. This equation will further reduce here, one of the a will get cancelled here. In numerator we have gamma square multiplied by area a divided by 2 times of n modulus. Integral of x square is same as equal to x cube by 3. Upper limit is L, lower limit is 0, so only upper limit will work. we have L cube divided by 3. So strain energy due to the self weight in a uniform cross section will be given as gamma square multiplied by A multiplied by L cube divided by 6 times of Young modulus E. Two members of the pin jointed truss is shown in the figure here. We have one member is AB and one member is BC. Length of member AB is given as L, and at the joint B we have pointed load is acting vertically downward, and the slope of the member BC is 3 vertical to 4 horizontal. Have the same modulus of elasticity E and the same cross section area A. Determine the total energy stored in the truss in terms of the load P, length L, Young modulus E and the area A. Since here we have two member, one member is AB member and we have second member is BC member is member 2. So you have to calculate here the individual value of strain energy in member 1 and the member 2. So total strain energy U will be equal to U1 plus U2. We have to calculate here the force in the member AB and the force in the member BC. In that case we have, since the area is constant, Young modulus is constant, so we can take out here 1 by 2 times of area multiplied by Young modulus, and what is left in the bracket is F1 square multiplied by L1 plus we have F2 square multiplied by L. Out of that L1 is known equal to L, L2 you have to find out. First you have to find out here what is this angle. So let's say this angle equal to theta. In that case we have opposite is 3, adjacent is 4. So we have tan of theta will be same as equal to 3 divided by 4. Take tan inverse here and find the value of theta. We will get the value of theta equal to 36.86. If this value is theta, then the adjacent value will be also equal to theta, and the alternate angle here will be also equal to theta. So this time the length L2 is a hypotenuse, L is a adjacent side, theta is known, so we can use here cos of theta. So we have cos of theta is same as adjacent length, that equal to AB, and we have hypotenuse is equal to BC. We are interested in BC, and BC is same as equal to L2 is equal to AB divided by cos of theta. That is, we have L2 is equal to AB is same as L divided by cos of 36.86. So we get L2 is equal to 1.25 times of L. So L2 is known. Next we have to calculate F1 and F2. To find out the force in the member B, you have to isolate this joint. So we will make the FBD at joint B, and we have only 3 members, so we can use the Lami's theorem. So let's represent here the point B first. One downward force you have to show, that equal to force P. Let's assume here the force in BC is in tension, so that force will show here, and this force is same as equal to F2, and this angle here between force F2, that is member BC, and horizontal is theta, and we have theta is 36.86. So this angle is 36.86. Also assume that the force in the member AB is in tension, so that force will show here. Tension force you have to show always outward. Let's say this force equal to F1. If this angle is 36.86, then this angle must be equal to 53.13. Total angle equal to 90, and the remaining angle here will be equal to 270. So we can apply the Lami's theorem. We have force P, and for the force P you have to write down the angle between other two forces, that is F1 and F2. This time the angle is 36.86, so we have sine of 36.86. Then we'll write F1. For F1 you have to write down the angle between other two, that is 53.13. So this time it is a sine of 53.13. Then we have to write down F2. So for F2 you have to write down the angle between F1 and P, that equal to 270. So we have sine of 270. So solve this equation 2 times and find out the value of F1. So we will get the value of F1 is equal to 1.333 times the force P. Similarly, we can calculate F2 as sine of 270 divided by sine of 36.86. So that value will be equal to, the negative value is negative 1.667. So we'll write 1.67 times P. One is positive and one is negative. Even it is positive and negative, is the square, so strain energy is always positive. Now this time we know the value of F1, that is 1.333 times P. L1 is equal to same as L. F2 is equal to minus 1.67 P. L2 is equal to 1.25 L. So let's substitute and solve this. You will get 1 upon 2 times of area A, Young modulus E, multiplied by F1 is 1.333 times P, square of it, multiplied by L1. L1 is same as equal to the length of AB, that equal to L, plus we have F2. This time F2 is minus 1.67 times P, so we have minus 1.67 times P, and we have square of it. L2 is equal to 1.25 times L, so we have 1.25 times L. Solve this, you will get this answer close to 2.625 times P square multiplied by L divided by AE. So approximately this answer is very close to 21 divided by 8 times P square multiplied by L divided by area divided by Young modulus E. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.